Keeping it safe. So this is the second principle of the last two. As I mentioned, academic labs are the last bastion of lack of safety that there is. And I would say that labs today are getting slightly better because there's been a number of very high-profile fatalities associated with laboratory work. And so keeping things safe are an extremely important part of being green. We're going to talk about hazard from a perspective of safety hazards and inherent safety or inherently safer design strategies. And I'm not sure how many people may have heard about things, and then conflicts and trade-offs. This principle, a great way to think about it is the same way as you think about the prevention of waste. All right? You have an inherent safety hierarchy, which is almost exactly like a waste minimization or a pollution prevention hierarchy. And a lot of the same thinking can be used to help you do this. So we should be celebrating because this is the last one, the last principle. And substances in the form should be used in a chemical process chosen to minimize the potential for chemical accidents, including releases, explosions, and fires. So, things do go boom. You know, we've had several recent examples, very graphic. The event in Texas is just one of two that's happened in the last couple months. And typically, we compromise safety and time in thinking about safety with the need to get on with what we're doing. So again, this quote, complicated and messy, simple and elegant. I don't have much time, so I'll go with the complicated and messy. And that's typically what we do. So again, kinetics, extremely important. We've talked about heat. Like I said, most of us in thinking about energy as chemists end up over here, which is the amount of heat in respect to time. And then the thing that we all dread are the runaway reactions. So we can have a runaway exotherm, which by far and away is the worst, but you can also have a runaway endotherm, and you can actually freeze things and break equipment that way. So either way, we want to avoid these kinds of precipitous events. Why do we want to do it? Because this is what happens. This is sort of the mother of inherent safety, Flicksburg, England, and there was a gentleman by the name of Trevor Klett who worked in ICI. And after this rather dramatic explosion, cyclohexane explosion, multiple fatalities, multiple serious injuries, critical injuries, really began to get the industry, the chemical industry, to think about how we can make reactions inherently safer. So I'm going to review a little bit about hazard, but from a different perspective than what you've heard about it. And it really is this idea that you have a physical or chemical characteristic that is inherent to the chemical that you're working with. And I mentioned very earlier on that most of what you work on is inherently hazard. And it's almost a rarity that something that you're working on isn't inherently hazardous. So we've got to get to a point where that is not the case. Ideally, we should be able to work in a shirt sleeves environment without hoods and do what we want to do. Hazards intrinsic to the material or its conditions of use. And here are some examples. Again, any one of these are kind of hazards. Most of us don't think about high pressure steam. From an industrial perspective, it's hugely important, but chemically, we're not so concerned about it. So inherent, eliminating the hazard by changing the process or the materials, integral to the product or the process or the plant. It's not easily changed, okay? So again, this brings in the notion that you have got to think about this from first principles. It has to be designed. It has to be part of your thought process inside your head before you even put pencil to paper or electron to computer. And water with a flammable reagent is a great example. This notion of something that is inherently safer, it's like, is it green or is it greener? And this is the same notion. Walk away today with that kind of an idea. It isn't absolute. We're incrementally making things better. That's where we're trying to get to. So it's safer. It may not be absolutely safe. So this inherent safety, this idea of after the system is perturbed, all right? So say you add too much heat or you add too much of an acid and you end up with an exotherm. It actually comes back to a safe and stable state. That's where you want. That's inherently safe. Inherently safer is that you eliminate it. You control the hazard. You don't create a situation where you're going to add too much of anything, heat or a chemical. So this particular design paradox applies to virtually everything in green chemistry. The place to make all the difference in the world is down here, okay? We may not know a lot about the process, but the opportunities for installing safety features, okay, really are there. We want to stay away from safety features. Really what we want to do is to have opportunities for inherently safer. And again, it's an exponential decay. We have to think about it up front. That means that we have to have an intimate knowledge of the materials that we're using and the reaction space. Okay, once again, I didn't say reactor, I didn't say round bottom flask. I said reaction space. So here is the connection between green chemistry and engineering and inherent safety, all right? Green chemistry, reaction paths, synthesis routes. This is really where you guys historically live. This is the kind of thing that you need to think about when you're talking about inherently safer design, okay? And it's, again, thinking through a variety of scenarios and potential hazards that are associated with your chemistry and your engineering design. So some principles. Intensification or minimization. What you don't have can't leak. So the emphasis is on simplicity. Substitution, which you again heard in your pollution prevention hierarchy, is the same thing here. If you can substitute one material for another, which is inherently safer, that's a good thing. Attenuation or moderation, less severe conditions, lower pressures or temperatures, right? Can we reduce the temperature? Can we run something not at reflex but heat it up just enough to get the reaction to go? Limitation of effects, changing the designs. Again, simpler. Simpler is usually better, but it's not simplistic. To do these things and to do them well requires a tremendous amount of thought up front. Okay? It won't be simplistic. So these are just some examples, again, that you can look at another time about simplification. This is a great example of simplification. The story is that NASA spent millions of dollars to come up with a pen that wrote in space. The Russians used a pencil. Right? Simplify. Why do we need a pen to write in space? We can use a pencil. So this notion about scale up I talked about before. This is historically what we have done. By the way, this gentleman, Dennis Hendershot, was quickly on the heels of Trevor Klett. Dennis worked at Roman Haas for many years, retired from Roman Haas prior to their acquisition by Dow. Great guy in inherent safety. Tremendous amount of publications, very knowledgeable. Semi-batch nitration process, again, this is how it's typically done. What controls the rate? Mixing, mass transfer, heat removal, rate and order and introduction of reactions. So what they came up with to replace that batch reactor and to try and avoid some of these issues was to come into a continuously stirred reactor. And again, order of reduction, reduce the size of the overall reactor. Rather than 6,000 gallons, it was a 100-gallon reactor, and they continuously siphoned off the product. Again, is it safe? Inherently safe? No. Is it inherently safer? Yes. There's another strategy, as I mentioned, is to scale out and number up. So this is something that with miniaturization we can actually get to eventually, is that we create small skid-mounted reactors and we just merely number up rather than scale up. And that allows us to get very close to what's this idea of lean manufacturing. You only make what you need, you only have small reactors to do it, and you number it up. So this gets back to that nitration reaction. Can we do it in a simple pipe reactor? And the answer is yes, we can. So there's the REPI process, a nickel carbonyl catalyst for acrylic acid. It uses acetylene, which is flammable and reactive. Again, acetylene we like as chemists because it's reactive, it's thermodynamically favored, right? It's hard not to react to acetylene, right? And it's kinetically, it moves very rapidly. And it also uses carbon monoxide, which is toxic and flammable. You all know you can burn carbon monoxide, right? And nickel carbonyl is exquisitely toxic. Anhydrous HCl, toxic and corrosive. So the product is a monomer, and that monomer is highly reactive. Acrylic esters and most polymers go through a phase many times of extreme reactivity. And again, because they're addition type reactions, there's a lot of energy associated with them, and they typically have exotherms, and those exotherms sometimes can run away. So it's very important to be able to control the chemistry and the exotherms. So can we do this by a different chemistry? Can we make the same compound? Well, we'll try propylene oxidation process. So we use a different starting material. We use oxygen and a catalyst. And is it inherently safer? No. But because we have some sulfuric acid as a catalyst, there's small amounts of acrolein as a transient intermediate, and acrolein is a very toxic material, and there's still this reactivity hazard. So again, it's better, but it's not exactly where we want to be. So an example of hazardous side reaction, forming perchloroethylene, or using, sodium hydroxide and ethylene dichloride as the solvent, vinyl chloride. We all use vinyl chloride to make PVC, very important material, industrially and economically. And they wanted to try a different solvent. Can we replace perchloroethylene? I hope so, because it's not a great solvent. And can we use a biodegradable hydrocarbon? Is that the best choice? Probably not, but it might be inherently safer. The reactants and products highly soluble in chlorinated hydrocarbon solvents, and the chlorinated hydrocarbon solvents are relatively inert, so that's a good thing. But what are the problems? Well, with a new solvent, reduced solubility, we might have an exotherm to deal with, and we have some engineering designs. So this is typically how industry manages these things. As it says, we want to run this chemistry, but it's going to require that we do some fancy engineering. Another approach would be to dilute things. So again, some of you like to use anhydrous ammonia. Is there an opportunity to use aqueous ammonia? And so on and so forth. Each one of these ideas are just examples of dilution that may be a better alternative for running the reaction. And again, this just gives you an example of the fact of dilution and the effect. So if you had aqueous ammonia in the distance of environmental effect, is diminished rather dramatically compared to anhydrous ammonia. So again, once the ammonia gets into the air, it's a problem. So simplification, again, is a very important concept. We tend not to think about the elegance of simplicity. And we think many times that if it's really complex, it must be good. And that's really not the case. It's harder to make things simple and make them run. So we can eliminate equipment. So again, this just shows you an example of a reactive distillation. It was all in the design of the reactor, rather than having this rather complicated series of reactors and extractions and so on and so forth. They actually did all of the reactions in a single reactor. And then they used some additional columns to remove impurities and heavies. So again, it's a simplification, and overall, it's an inherently safer approach from an engineering perspective, but it requires a tremendous amount of process understanding and process control to make that work. So again, it is simpler, but that reactive distillation column, as I mentioned, is more complex. Multiple unit operations in a single vessel. It's more complex to design. It's more complex to operate and control it. So that particular single reactor has a greater tendency or possibility of going boom if something fails. So single complex batch reactor, again, is an example, or a sequence of simpler reactors to do the same thing. Just another example of simpler approaches. In that example, each vessel is simpler, but now there's 3 vessels, right? And rather than a single column or a single reactor. So it is simpler, but it is, again, a series of trade-offs, and you really need to understand the specific hazards and the trade-offs that you're making. So here are some problems that we end up. The properties that make the technology hazardous are also many times the properties that make it useful. So here's a great example. Airplanes travel at 600 miles per hour, gasoline is flammable, chlorine is toxic. The control of the risk is the critical issue. There's multiple hazards. Everything has multiple hazards. Again, the way we're doing chemistry nowadays, everything is hazardous, right? Which means that there's an inherent risk of exposure. And again, the simple example is automobile travel versus other forms of travel, and the inherent toxicity or the inherent hazards associated with those particular modes of transportation. So I'm running out of time, so I'm going to click through this notion of inherently. So can I eliminate the hazard? If I can't, what is the magnitude of the risk? Do the alternatives justify the risk? And are there additional systems that I have to put in place to manage that risk? So I hope, oh gee, this is the wrong one. I hope that I've given you an overview of inherent safety, a better understanding of some of the trade-offs that you run into. I hope you understand a little bit better about the inherency associated with materials and the importance of designing to eliminating or substituting, or at the very least minimizing, some of the hazards that are associated with any process that you run on a daily basis. And with that, I will end and ask you to find your last exercise, which is really a reflection and a discussion